Oh, hell yeah. So what we have here is finally the holy grail of particle motion in circles. Polar coordinates, I think you get it. But here, you know what I mean? Where'd I get this? You know what I mean? Shams, you know what I mean? Engineering dynamics is crazy, you know? But this is the equation in there. It looks ridiculous. And we don't even need, you know what I mean, just r dot dot, the acceleration of the radius, plus 2 times the velocity of the radius, but times the angular velocity, okay, plus the radius times the angular acceleration. This is in radians per second, this is in radians per second. This is change in radians per second, change in time, change in okay, anyway, minus, this is the tension in the string, you know what I mean? If we're on Earth, or you know, we got about a pint glass pulling us towards the center just to make sure we're on course. Anyway, more on that later. But anyway, so the crazy thing is, most of your problems, you know, the radius isn't expanding, you know what I mean? You're not rotating like a balloon, and then someone's blowing into the balloon and it's growing or something. So, you know, usually the radius won't have an acceleration, the radius won't have a velocity. So for a lot of problems involving circles, hey, it's just angular acceleration and then just your speed. Like this is just RPMs. This is radians per second, yes, but that's the same thing as revolutions per minute. You know, kinda, conversion factor, or RPMs, revolutions per minute, revolutions per second. Anyway, I think we get it. So if your saw is stopped, well, and then you turn it on, it went from 0 revolutions per minute to 5,000 revolutions per minute. So you do have, and maybe that took 1/10 of a second. Okay, so let's just do this real fast, because this is a prerequisite for this problem. So you're saying that my saw goes from 0 to 5,000 revolutions per minute. Well, how many revolutions per second? Well, you got to divide by 60. How about this is 6,000 divided by 60? Perfect. Well, because I know, get rid of a 0, so this is 600 divided by 6. Okay, get rid of the 6's, it's 100. So there's 100 revolutions per second. Okay, now we're getting somewhere. And how many radians in one revolution? So how many radians are in a circle? Well, a circle is 6 radians, or 6.28. It's 2 pi radians. Oh, okay. So 100 revolutions, well, times 6, well, that's like 6, well, it's 628 radians. Okay, or 600 radians. Okay, I get it. Okay, we get it. Okay, but guess what? You went from 0 to 628 radians in 1/10 of a second. You know, probably faster, but now about 1/10 of a second. Maybe if you've got a slow saw, it's like, you know, full second. But let's say you got a fast saw, just like, poof, instantly goes. Okay, so what's your angular acceleration? Well, angular acceleration is change in radians per second. So we went from 0 to 600, and then change in time. Okay, so we got 628 radians per second. That's our change. And change in time is 0.1 seconds. Whoa, we're dividing by something small. So we get 6,280 radians per second. So we're changing our velocity by 6,000 radians every second. But that acceleration only takes place over 1/10 of a second. A very small segment. Okay, so I guess we understand what these simple this is the simple part. But now this problem is holy grail, because we got to talk about our radius having velocity and our radius having an acceleration. How do we do that? Well, we throw a rod that can spin around a point, and we throw a heavy gosh darn washer on there. Now, is this a vertical rod? No. We'll just pretend it's horizontal. You know what I mean? We're spinning the roulette wheel of this rod, and the washer's winging off, and it's spinning that way, I guess. Oh, damn it. They said the acceleration. Oh, they're saying the angular acceleration is that way. Oh, I did not notice that. Okay, fair enough. So, get this. So the angular velocity is 5 radians per second that way, but then they're saying its angular acceleration is 10 radians per... Oh, is this thing slowing down? I did not know that. I thought it was speeding up, but no. The angular acceleration is that way. My bad, I did not catch that. But we haven't even started this problem, so let's do it. All right. Okay. Yeah. But it gives us some information. It says that this washer is flying off this thing. It's going 4 meters per second. Well, this is only a 2-meter rod. You know what I mean? And it looks like you got less than 4 meters here. So if this is 1 meter, this is 2 meters. Well, we're just going to call this 3 meters. So if it's going 4 meters per second, if you allow this thing to go 1 more second, well, this thing's probably just sayonara. You know what I mean? And how much time is it going to be sayonara? Well, it would go 4 meters in 1 second. So look, in about 1/3 of a second, this thing's flying off. Okay, we get it. And then there's another piece. Its velocity is 4 meters per second at this point, but it's speeding up because it's got an acceleration by 3 meters per second along. So it's increasing at a rate of 3 meters per second in that direction. And that's the crazy thing about physics. You're like, okay, I got position, I got velocity, and I got acceleration. Well, you know, let them work for you. You know what I mean? You're the boss of them. Okay, so how are we going to make this simple? Because, well, this is perfect. Because, check it out. We have an acceleration in the radius direction. Yeah, we said that was that. So this is our dot. So we got that. So we got, and then does our radius have velocity? Sure. There's our r dot. You know what I mean? We got a velocity at 4 meters per second. We already got these two. Perfect. And do we know what omega is? Hell yeah, that's 5. Okay. And do we know what the angular acceleration is? Yeah, that's 10, but it's the other direction. So we're going to call this the negative direction, and we're going to call this the positive direction. We're going to say that's negative 10. Perfect. Okay. And then this is always negative towards the origin. Okay, and this is, hey, do we have a radius? Yeah, okay, so I think we get it. So you literally could just plug and chug. And that's what they did. But this book is so dumb because they chose to do something different. They're like, oh, well, let's call it the Coriolis acceleration. I mean, it took me like 3 months just to be like, okay, I got this down. My radius can accelerate. The radius could have a velocity. And then the radius is just the radius. Perfect. You know what I mean? But then they made it so damn confusing, and it's the same equation. You know what I mean? They just made it dumb. And they said, oh, it's the Coriolis acceleration. Well, okay. So you're saying the 2 omega v is the Coriolis part? Well, fine. This is the Coriolis part. 2 omega v, because r dot is v. Okay, perfect. So this, you just call it the Coriolis. Who cares? I mean, that's for another 3 months of scratching my head. But alright, let's do this. Okay, so how could we do this easy as potatoes? Let's say we did not have this equation. You know what I mean? So that's where we're gonna go. So I'm gonna take this sheet of paper and we're gonna put it to the side. We'll get our problem like right here. We're just gonna get the good part of the problem. Okay, because this is interesting. Hey, it looks like this thing's going to fly off, right? And what's the... Well, this was the confusing part. The acceleration is back this way. So I was just like, what? You know what I mean? Hey, it's going to fly off this direction, and it says it's going to fly off faster. But this is where circles are circles. You know what I mean? The fact that it's connected to a circle, in a little bit of time, it's going to be right there. Wouldn't you agree? And so, you know what I mean? It's, so you do have stuff going this direction. That's all I'm saying. You know, so even if you're doing circles and everything looks like it's going to fly off, you are going this way. Because, I did it like this. Well, let's say you get shot out of a cannon on Earth. So we're just going to do this. You get shot out of a cannon on Earth, and in the second you get shot 100 miles per hour straight up, the Earth is spinning at 1,000 miles per hour that direction. So you're literally, our velocity is like 1,000 miles to the side. You know what I mean? Like, if you're at the equator, but you're just like, whoa. Okay, and let's say gravity just got turned off instantaneously. At the same time you got shot out of a cannon. Well, two things are going to happen. The Earth stops. Let's say the Earth stops rotating and no more gravity at the same time. Well, you're going to go 1,000 miles that direction, and you're still going to go 100 miles up. But mainly, you're going to go that way. You know, it's going to feel like you're going sideways. This up component ain't no thing but a chicken wing. So so you got to look at that when you're doing rotational problems. Is like, oh, is my speed this way a lot crazier than my speed this way? So how do we find the speed this way? So because it's spinning, it's got a velocity that direction, and velocity that direction is just this omega, you know what I mean, your radians per second times your radius. Because anytime you see radians per second, anytime you see the word radians, just say radians times radius is something useful. So alpha is equal to negative 10 radians per second. Well, times by the radius, 2 meters, and we get negative 5 meters per second squared. That's just normal acceleration. Okay, I can dig. And then if we do the same thing, 5 radians per second times 2 meters, well, that gives us 10. So our velocity is 10 meters per second that way. So wait. You're saying in 1 second, this thing, and this is 2 meters, and then so there's 2 meters. Whoa, you're saying in 1 second, this thing's going to be way up there? Like 10 meters away? Well, hell yeah. So in 1 second, this thing is going to be 4 meters that way and 10 meters that way if it just decides to instantly let go. So at this moment, if this washer breaks off this assembly, well, it's going to want to go 2 places. It's going to want to go 4 meters that way in a second and 10 meters that way in a second. And it's the same thing here. Yeah, you're going to go 100 miles an hour that way, 1,000 miles an hour that way, and then you're going to be on that. So yeah, you're going to be in 1 second you're going to be 10 meters this way and then 4 meters up. So you're going to be like right there. So you guys should keep it in view. Can you see nothing? Okay. All right. So I think we got that part. And that's a critical part there. I mean, I never thought of that. I never thought this speed dominated. Hell yeah, that's going fast. And the fact that this washer's lifting off this rod, well, it's a little bit less, but they're about even, 10 and 4. Okay, so let's continue on before this picture just gets messed up. Okay, so what's the next thing we want to do? Oh, check this out. I think we can get right to the answer if we say, well, okay, and this thing's spinning. So the other thing is like, okay, this thing's spinning at 5 radians per second. What the hell does that mean? Well, I said a circle has 6 radians. So 1 circle is equal to 6 radians. So if I'm spinning at 5 radians per second, well, that's about a circle. So every second, I'm almost going around a circle. You know what I mean? And what's a radian? Well, it's 60 degrees. So that's 180 degrees, 60, 60, you know. If you ever played that trivia game, you know, I don't know, it's like the Pursuit of Trivia, something like that. Anyway, they have those little 60-degree wedges. So, but yeah, that's 1 radian. Okay, so every second you're going to be doing 5 of those. Okay, so in 1 second this thing is going to be spinning all the way around and over there. So you don't use 1 second. Okay, so we're going to use 1/10 of a second. Because in and that's the other thing. Our speed is 5 radians per second times radius. That's going to be 10 meters per second. That's our velocity this way. But in 1 second, we're going to reduce that by 10 radians per second. So 5 goes to -5. Obviously, this thing's going to be stopped. So in 1 second, it's going to be stopped anyway. So actually, 0.5 seconds, it's going to be stopped. Because in a half a second, so how far could it, so if it's right there, and we're going to go 2.5 radians, so right there is when it's going to be stopped right there. Okay, so that's why we're just going to do 0.1 second. Okay, sounds good. So in 0.1 second, how many radians is it going to go? Well, it's going to go 0.5 radians. And you need to tattoo this one on your chest. You need to know that 0.5 radians is 30 degrees. Because now 0.25 radians, well, that's 15. You can easily get there, you know what I mean? But anyway, because 1 radian is 60 degrees. Okay, so we're just more basics, you know, get that dialed in. But okay, whoa, this is 45 degrees. So you're saying in 1/10 of a second, this thing's going to be right there. You know what I mean? This little washer is going to be right there. Fine, we got it. And, well, in 1/10 of a second, it's going to be, you know, all right, this is 2 meters away. But like I said, in 1/10 of a second, it's also going this way. So it's going to be 0.4 meters. So if this is a meter, 0.4 is like right there, and if it's right there, it's going to be so it's going to be 2.4 meters. So there you go, and but you could do the acceleration too in 1/10 of a second. Well, that's why we used a very small snippet in time. You know, 0.1 seconds actually isn't very good. It's too large. We would want to do a 100th of a second. But we're just guesstimating. All right, so, okay, yeah. So in 0.1 second, we're going to be right there. Shoot, but we definitely want to know acceleration. And acceleration is change in velocity over change in time. So we know we're taking 0.1 seconds. But what's going to be our change in velocity? Oh, perfect. So our velocity here, yes, is 4 meters this way, and then 10 meters that way. So do that. So it's 4 meters this way, and then 10 meters that way. And then we figured out what the hell that is. And, you know, just the resultant of that, you got to know this. 4 squared plus 10 squared, square root of that. And let's type it in. That's going to be 16 plus 100, square root of 116. So this acceleration is 10.77. No, sorry, shoot, this is velocity. Excuse me. Because this is the velocity. So your velocity is 10.77 meters per second at this point. So now we're going to go over here and check this out. We said in 0.1 seconds, our radians is going to reduce by 1 radian per second, because 0.1 seconds times negative 10 radians per second, well, that's going to be a reduction of negative 1. So 5 radians goes to 4 radians per second. Okay, but our radius, radians times radius, our radius moved to 2.4, so you got 4 times 2.4. Hey, that's 9.6. Oh, okay, so that's kind of the same. So 9.6, so meters per second is velocity. Sorry about that. In that direction. And then what's our new velocity trying to fly off? Well, it's going to increase by 3 meters per second. We're not increasing, we don't have a second, we got 1/10 of a second. So it's going to increase our velocity by 0.3 meters per second. So it's going to go to 4.3 meters per second. Oh, perfect. So you're saying right here, now we got 4.3. Okay, perfect. So 4.3 squared plus 9.6 squared, and you got to know this. You know what I mean? You got to know, hey, I got a direction this way and a direction that way, and what's the magnitude? What's the magnorama? So 4.3 squared plus 9.6 squared, square root of that. Oh, okay, so it's a little bit smaller, 10.519. Okay, sounds good. So it looks like we're going to have a reduction in our acceleration. So change in velocity is negative, and change in time. So that's going to be 10.519 minus 10.77 divided by 0.1. And we're gonna store that as alpha b. So this is b, and then square root of 116 stored as alpha c. This will be alpha c, and then so alpha b minus alpha c divided by 0.1. Hell yeah, we get an acceleration of 2.51. We get an acceleration of negative 2.5 meters per second squared. Ah, dang it. All right, I apologize. You know what I mean? The answer is, you know, what the hell is the answer? I mean, the answer is an acceleration of 51 meters per second squared. So we're nowhere near that. So let's just do it, well, like, you know what I mean? That equation is what we want. So we want the acceleration. The radius is accelerating. Well, we already said that. So we're going to put this up. The velocity, the velocity, yeah, the velocity is increasing at a rate of 3 meters per second. So that's the acceleration this direction. That's the acceleration of the radius. So we got 3. But then the crazy thing is you need to put these in the direction. So we need the direction of the acceleration, the direction of the radius, and the acceleration tangent. You know, I guess that we're calling that phi. So here is the direction of the radius. So we're going to do those. So we got 3 minus, well, 2, and then 5 is going, this is 5, acceleration is negative 10 radians per second. So this is 5 radians per second, and we're squaring that. Okay, perfect. So that is going to be 2 times, so we got 5 squared times 2, 3 minus that. So we got negative 47. You know what I mean? The acceleration is in this direction, negative 47 meters per second squared. Now the acceleration this direction, well, we got that slowing down. So there's 2 components there. So those components are those 2. Yes, it's actually just slowing down. So we'll do that one first. So the radius is 2, slowing down negative 10 radians per second squared. You know what I mean? So that's going to be negative 20, and then we're going to add to it this. I guess this was the Coriolis effect, but 2, the velocity. Well, what's the velocity of the radius? Well, it's 4. It's 4 meters per second. This thing's going that way, 4 meters per second. And I guess it all just works. I was just trying to find just an easier way to do all this stuff. And then 5 radians per second. So we got 5 times 4 is 20. That's 40. So we got 40 here. So you got, yeah, so then you got 20 in the direction of positive directions. This was negative direction, positive. So yeah, perfect. So you got this direction, you got 20, and then this direction, you got negative 47. Okay, so and then so 20 squared plus 47 squared, square root of all that. 20 squared plus 47 squared, square root of all that. And there you go, 51 meters per second squared. You know, they tried to do a really weird way using the Coriolis effect. They just called it Coriolis, but just that part is. So I'm just going to say, hey, is this accelerating? Yes, your radius is accelerating. Is this got a velocity? Well, sure. If it's accelerating, it's definitely got this component too. So if it's got this component, definitely got that component. But if if it's fixed and the radius don't change. If our radius don't change, hell yeah, you just those 2. But I was trying to find that quick little way to be like, well, if the point is here, you know what I mean, and then a second later it's here. Well, if we just have positions, change in position over change in time, well, hey, we can get the velocity. And then if we got the velocity of that point, then we could do that thing again, change in position, change in time, and then we could get a velocity of that point. And then we'd have velocity 1, velocity 2, and then you could get accelerations, just change in velocity, change in time. So that's what I was trying to do, but I was not successful. Absolutely not successful. I'm going to review that because I definitely want a simple... I mean, I guess I can just memorize this equation, but I've spent a couple months just trying to actually figure out where these terms come from. Like, I get where this terms comes from. I've done a video on that. This one is super obvious. Yeah, you have an a saw's got teeth, and you just pretend like the saw is just a straight line. And yeah, it's accelerating. It's going from 0 to hella fast. We get that. And then this one's a little bit different. This one's saying, hey, this particle should just go in a straight line, but it doesn't. It goes actually back towards the radius. you know, to keep it around the circle. And we've done that one before too. But these, and this one makes sense. So I guess it's just this one that don't make sense. But the crazy thing is this one is two components. One in the changing radius direction and one in the direction of the, you know, of the angle. Anyway, I'm fine leaving you confused because I'm gonna get better at this, and but at least just use that equation, not the Coriolis equation or whatever. That thing's crazy. There it is. They want you to do it that way. That was kind of confusing in the book. That's dumb. Just do it that way. All right, that's another one. Not a very good one, but that's a video.